Hello. In this session, I'd like to talk about the experience of having built the largest storage in line. I'd like to briefly introduce myself. I am Ilsoo, in charge of Ceph Storage DevOps in the Cloud Storage team and Line Plus. Nice to meet you. You may wonder what the screen is all about. I'd like to explain. In operating the Ceph cluster, I had many opportunities to contribute to open source community. Ceph distributes the t-shirts with the names of the contributors every time a new version is released. And so this is a picture I took of the t-shirts that I received from the Octopus version up to the current Quincy version. So this shows the pleasant experience I had in having participated in the open source project. This is going to be the order of my talk. I'm going to talk about why we began to think of the hyperscale object of storage. I'd like to talk about the background first and why it was difficult to solve the problem with the Ceph single cluster. And then I'm going to talk about the solutions and some of the optimization items that we proceeded with. And now about the background of the project. In Line, we store many formats of data, and image and video take up a lion's share. The size is in several kilobytes to several gigabytes. And we also store the metadata, and those files are in the range of tens of bytes. The size variability means that it's difficult to manage from a storage perspective. I'd like to talk about one of the considerations that we had in designing the hyperscale object storage, which is difference in the size of the data stored. And the total size was hundreds of petabyte, and the number of objects expected to be 300 billion. So this is quite a huge scale. If you were to fill up all the racks with the servers, then it would require about 80 racks. So this is quite huge. Basically, in order to store the data as a solution, we selected Ceph. The reason we went with Ceph is for a very long time it has been proven its scalability and reliability. And because it is open source, relatively, it is of a lower cost. Of course, it doesn't mean that you can just download from the internet and install and you will be done. No, in order to operate open source, you need to have internal resources that understand and can handle Ceph very well. So it means that it may not be economically feasible at a small scale, but as the scale grows, then it makes economic sense to have Ceph. This table compares the open source storage, and it is public data, but I think there are some inaccuracies. For example, SAN does not support Ceph, but rather supports at a block level storage. And as for Cinder, it is not storage, but it is a system that manages other storage. At any rate, as you can see from the table, Ceph does provide the most various types of storage services. And this could be a major issue because if you were to provide storage in various formats, and if you were to use heterogeneous solutions, then you would need to hire separately the professional resources. But as for Ceph, the Ceph professional staff can cover the variety of services, and that is the strength of Ceph. Within Line, this is the Ceph cluster that we have built. There are 30 independent clusters and a total of 2,500 plus servers. And as for the number of OSD daemons, in other words, the number of disks that store the data is more than 70,000, and the raw size is higher than 700 petabyte. And I don't think there are many Asian companies that have installed and are operating such a large Ceph. But what I showed you is just independently configured clusters per purpose. And today I'm going to talk about when one huge cluster is of mass scale. So what do I mean by mass scale or hyperscale? The current cluster size is hyperscale, and you can see the numbers: 3,000 disks, 150 servers. The total size is 20 petabytes. So we have the size of 10 clusters. So it's not one, but the size of 10. Why do we not call it one big cluster, but 10 clusters? That is because it had limitations in configuring it as one single cluster. Ceph does have good scalability, but it does have its limitations. When it reaches a certain size, the components in Ceph sometimes become unstable. Within Ceph, there's a component called Ceph Manager. It stores the status of Ceph cluster, collects the metrics, and manages the plugins. But structurally, it has its limitations, because even if you have many daemons, it's just one that is active and the others are waiting in a standby mode. And when the active daemon dies, the standby daemon takes over. And that means however big the cluster is, all the OSD status has to be collected and managed by just one daemon that is active. So as a result, when the critical mass is exceeded, the Ceph manager continues to die or creates erroneous information or returns erroneous information. And I'll talk about the explicit example in the next slide. And there are rare Ceph monitors, so there are rare issues created by Ceph monitors because of erroneous client issues. The memory of the monitor continues to increase and then is killed out of memory. But this is not that serious because another daemon would take over. But there was a serious issue considering related to this, and I'll talk about this in the later slides as well. This shows that when you increase the number of OSD to 4,000, the graph collects these metrics, and you can see that their graph is discrete. So this means that Ceph managers die periodically when there are 4,000 in a cluster, and when there's a change in the placement group, the Ceph managers cannot withstand it, and they continue to get killed. And they cannot show the status of the Ceph cluster properly. And of course, even if the Ceph manager dies, the function of the cluster is still intact. But in order to manage such size, you need stable monitoring. So in that sense, these issues could cause problems. And this is an actual case that we experienced when in the three Ceph monitors, when all the daemons could not respond, the total cluster had an issue. As you can see from the left-hand side, it looks as if all the OSDs are down, and as you can see on the right-hand side, there is a cut in the graph curve. During this time was when the Ceph monitors had problems. The failure continued for about 30 to 40 minutes, and the storage was not related to line message. It was just for internal purposes. So based on these experiences, line message storage is being maintained in a stable manner. So going back to my main point, the problem was caused by a bug in the Ceph monitor. And this is related to the internal mechanism, and I'd like to explain for better understanding. The cluster status of the Ceph is stored in OSD map, and when a cluster node is added or deleted, the OSD map is changed. And to trace the changes, the OSD map has a value called epoch. Let's say there are 3 OSDs, and if the epoch of OSD map is 1, then when you add one more OSD, the epoch of OSD map becomes 2. So the history of OSD map is stored in the monitor. But you cannot hold on to all the history limitlessly, so the basic value is about 500 to 750. And when it goes beyond the range, then it is trimmed or deleted. And when you see this graph, it is mostly underneath the line, but the orange line continues to increase. So you sometimes get circumstances in which trimming does not take place properly, and then you get a late commit, and sometimes the Ceph monitor cannot respond. And there are three monitors, and if one cannot answer, the other monitors could take over to maintain stability. But in this case, that action could not be taken. And the Paxos protocol is the one to use for synchronization. And then there was commit, and there was simultaneous problem that occurred. And as the scale grew, this problem arose. This has been solved with a batch, and we're continuing to monitor the value, and we're managing it adequately. So up to now, I talked about such episodes, and I'm not saying that Ceph is unstable. It is excellent in stability and scalability. So that's why we are continuing to use Ceph. But it does show that when the scale grows, there could be possible potential problems. This shows the lesson of don't put all your eggs in one basket. So through this experience, we learned that there is no one perfect solution. And what we are planning to do is a hyperscale storage, and it is risky to configure it as one single cluster. Ceph is very good in a certain scale, and that certain scale is by no means small. But when it exceeds the threshold value, then we do have the possibility of coming across unexpected problems. So it is important to partition the cluster into manageable units. So in other words, we use several baskets instead of one. And we took these into considerations in designing hyperscale object storage. It has to store up to hundreds of petabytes of data, and it has to be scalable in a sustainable manner. So scalable up to and beyond the threshold value. It has to be fault tolerant, and it has to have S3 compatibility. And as the cluster is quite huge, we have to think about the cost of data storage. It has to be effectively managed. And we have to satisfy all these conditions, but to the user, it has to look like a single cluster.
Then I'll show you how we have approached this. The first is to split the cluster into multiple clusters, but make it act like a single cluster by creating an abstraction layer. Which means that we have created a cluster of clusters. But there have been some constraints that had to be applied. First, the number of backend clusters should be increased, and the existing clusters cannot be removed, and weight can be changed, and data reshuffling or data rebalancing is not allowed. Now, this picture shows how we have configured the cluster of clusters. At the bottom, there are Ceph cluster and load balancer. And this is a single cluster that independently are activated. And there are multiple such independent clusters, and there are about 10 clusters. And we have created an Nginx-based routing layer. This is not a simple reverse proxy. There are some added work to be done at this layer. For example, the routing layer has to determine which cluster will handle the traffic for particular buckets, and the traffic had to be controlled based on weight. and at the bottom, multiple clusters are present, and the traffic for these clusters cannot be equal every time. Sometimes there would be storage capacity differences. So the upper layer controls traffic based on weight, and this routing layer has to receive massive traffic, so it has to provide scalability through multiple LBs and DNS round robin. And as I have showed you before, these are independent clusters that stores the data, and data durability, data replication are performed in each cluster, and replication between clusters are not performed. So let's see which cluster handles which user traffic. As I have mentioned in the constraints part, the configuration of member clusters that configure these clusters will change with time. In order to track these changes, the router layer keeps the cluster map. In this cluster map, there are member clusters that configure the clusters and weight value for the member clusters. And it also have the epoch value that grows with time. So this picture depicts this aspect. First, there are 2 clusters, but then it grows and expands to 4 clusters. And in order to deterministically decide which bucket uses which cluster, we keep information on which bucket individual epochs belong to. So when there is a traffic for a particular bucket, the cluster map belonging to the bucket is determined, and based on the hash value for the bucket name in the cluster map, the cluster will be chosen. So the bucket A, B is distributed to cluster 1 and 2 in the picture, and bucket C, D to cluster 1, 2, 3, and 4. So with the cluster map change, the epoch value increases, as I have mentioned before. The epoch value increases in 2 cases. First, when a new member cluster is added, and second, when the weight value between member clusters are changed. So with this, even if the cluster configuration changes, user traffic will be chosen or defined deterministically which cluster will be used. So the weight value is adjusted, and we can see that more traffic is sent and forwarded to cluster 1. Now, since this is an object storage, it uses the S3 protocol. S3 is an HTTP-based protocol. The routing layer will need more than reverse proxy. It needs additional features. Most of the requests can be working properly if it is forwarded to appropriate clusters. However, for copy requests, forwarding alone is not enough because of the Ceph's internal logic that handles copy. As you can see from the picture, the object that is stored in Ceph is partitioned into different objects, and the first object is the head, takes on the role of the head. So the tail, the number of tails and the name of the tails are stored in the internal metadata, and copy requests will be made on this object, and then the Ceph's RedOS GW will create a new head, and it will be sharing the object tail. With that, data copy will not be made, and that is a strength. But in our scenario, that becomes a problem because cluster boundary could be changed. So since ours is a cluster of cluster, when there is a copy request made for the object that exists in other clusters, we cannot handle it from the Ceph's RedOS GW. The error will be returned. And when this becomes a multi-part request, things become more complicated. When S3 uploads multi-part object, it goes through a more complicated process. Init request is sent, upload ID is acquired, and the part is forwarded. And then a complete request is sent that completes the object request. However, this part in the middle could be a copy of another object. So this adds to the complexity. So we need to comply to these processes, and we also need to perform the copies between the clusters and handle the request at the routing layer. Last but not least, we'll have to talk about why reshuffling is ruled out. We can see from this picture that the truck has too much load and it is stranded, and that shows that is a metaphor of why reshuffling is ruled out. So about reshuffling, the cluster, a single cluster adds a single node. Then in Ceph, it goes through reshuffling, and nodes objects are migrated to a new node. Then there is a traffic rebalancing issue. So I think this is not feasible. So when a cluster is this large, adding a new member cluster is a completely different story from adding a node to a single cluster. It's about adding a large cluster, and reassigning object to this will take a lot of time, so it is not feasible. And the added unit is a cluster, so even if there is a concentration at a certain point, the traffic of the users can be handled appropriately, and it can be scalable. So I have mentioned about federating multiple clusters. Now I would like to talk about how we can raise storage efficiency. So we are dealing with a large cluster, so it incurs a lot of cost. So in order to reduce the cost, we have to find a way to raise storage efficiency. So we have taken a hybrid storage approach. SSD, HDD, replication, and eraser coding methods are all mixed. It is not a tiered method. We check the object size and choose the media for storage. This is not a default function in Ceph. This is an added function that came out of our own need. In general, when SSD and HDD are mixed, a tiered storage structure is adopted. Hot data is stored in SSD, warm or cold data is stored in HDD. We do not take this method because we considered the traffic characteristics that we receive. We have applied 423 EC to HDD because it is more cost efficient than maintaining 3 replications. However, if this is applied to the real cluster and if a small object is stored in EC pool, the overhead is quite large. And the traffic that we receive accompanies small objects that includes a metadata for each object. So we cannot just simply look at whether it is hot or cold. In that way, we cannot raise data storage efficiency. So we have opted a method where we can select the media or storage method depending on the object size. So this is right for our data characteristics. Metadata object is a small object, and there are frequent requests, and it is sensitive to latency. So we store this to SSD, and the large objects have less sensitivity to bandwidth and latency. So we thought that it would be good to store in HDD. Last but not least is a lifecycle based optimization. We have a lot of data, so erasing or deleting it well is as important as storing it. And the data, the size that we have to delete increases with cluster size. So when an object reaches its lifetime, then it had to be deleted properly. But in Rados GW, there had been some problems. The bucket list has to be partitioned to each individual shard, and each thread handles each individual shard. And in that case, the specific shard that stores the data will take more time to handle that shard. The thread that handles that shard will take more time than other threads. So if you see the picture, shard 1 has a lot of objects that it needs to delete in bucket B. So the buckets in shard 1 will take time to handle the deletion. So it will take days of time to delete it. So days worth of data will not be deleted. So we needed multiple work threads to enter and handled in a single shard. So that's how we modify the Rados GW. So just like before, a single thread can also handle a single bucket. That's how we have modified our approach. Now, the key takeaways. We have been operating Ceph. It is a very reliable and scalable open source storage. However, it cannot scale indefinitely. It showed problems when it reached a critical mass. So in order to solve this issue, we have federated multiple clusters and make it act like a single cluster to secure S3 compatibility. And the method to store and delete data have been optimized to raise cost efficiency. So we were no longer constrained by the limitations of Ceph, and we were able to create a hyperscale object storage which can be scaled continuously. Well, thank you for listening. Now we will move on to the Q&A session. If you ask your questions, I will try best to answer the questions.
Thank you very much for the presentation. We will invite the interviewer for the further discussion. We will also take questions from the online audience as well. If you have a question, please use the question mark on the bottom right of your screen, and you can post your questions there. We have as the interviewer Numata Koki from Yahoo Japan. Please introduce yourself briefly. Hello, I am Numata from Yahoo Japan. I am in charge of validating new storage technology. Thank you. Listening to the presentation, if there were any questions, please pose your question. First of all, it was quite interesting and informative, so thank you for the presentation, Mr. Ilsoo. What I was concerned about most was the abstraction layer. In the abstraction layer, we do work with many communities, but as for creating the abstract layer, how many process steps were taken, and were there any headaches that you had to suffer from? Yes, what we focused on was performance, and on top of that, if we added the abstract layer, we couldn't manage to lose performance. So we were mindful of trying to keep the performance. So that meant we had to keep the abstract layer as thin as possible. In implementing Ceph, we had a deeper understanding of the related protocol. So we did not try to compromise on the requests, and then we built the abstract layer on top. So the amount of code was not that voluminous, and it took more time to design. But as for the abstract layer and implementing it, it took about 2 to 3 months.
Thank you. So you have been able to do it in just 2 to 3 months. I think that's great. And there are many other questions. In terms of data protection, I think there are some clusters. There are clusters in the bottom. The data enters the cluster called bridgehead or the hub, or I wonder if it is included in a single AZ or in multiple AZs. Well, this is configured in a single AZ. And as we operated the storage, we focused on reliability. So we adopted a remote DR. We did the data replication from remotely, and that is a feature included in the Ceph. And we tried to apply it to a wider scope. And that's what we are working on.
Is the backup of DR asynchronous? It acts close to it. Thank you.
So we also do transverse hub implementation and to configure using AZ. So we would like to collaborate on this technology. Could you wait for a minute? We have a lot of questions, so I have to choose from them. This is a very good opportunity. The routine component in the cluster has to be designed for SQL out. Is that the case here? The cluster map plays that role. If there are 3 clusters, and if there are 4 clusters, the bucket distribution would be different. If we're just doing hashing and routing, the locations will have to change. Then the data location will change, and that will be a problem. In order to make up for that, the cluster map of a certain time will be saved. And when the cluster increases, the bucket is forwarded according to the cluster map. And when the cluster is expanded, then a new cluster map will be created, and the buckets will be defined anew, and the bucket will be forwarded and distributed to a new expanded map.
Thank you very much. There is one additional question I have. In storage, Ceph may have good performance, but as for data migration, maybe is there anything that you're paying more attention to, and what is the actual condition of operating it? Could I clarify your question about which part of data migration you are talking about? So let's say a new server becomes old and you have to maintain it. So for maintenance purposes, you have to migrate the data. So what kind of methodology are you using for data migration? Yes, it is cluster to cluster. So one member cluster is the Ceph cluster, and that Ceph cluster is when you have additional or deleted member. We do have a backup plan, so it automatically does rebalancing.
Did that answer your question? Yes, I think that's the Ceph's function. Thank you very much for your answer. And last but not least, the timing of the scaling. The storage monitoring how can it be scaled? And when a failure occurs, how can we know that? Is there a monitoring system for that? I wonder if there is a unique way that Line adopts. Well, I would like to talk about the monitoring system of Line. One is related to performance, and the other is about log. Prometheus and Elasticsearch store these related data, and when there are any failures or any unusual event, then alarm will go off. And there's a pager solution as well. So the alarm is sent to the persons in charge. And in the team, there are 2 people assigned to the pager duty. So these people are in charge for that pager duty. So when there is a event on that cluster, then the pager duty persons will handle the event, and when there are more work required, then the pager duty persons will contact other people to handle the issue. So you have mentioned about the alarm policy. I think I forgot the first question. What was the first question? About monitoring or surveillance. System surveillance. I wonder if Line has its unique surveillance method. Since the cluster is large, the surveillance is another big topic. There are separate developers working on this, so the performance metrics are stored and the logs are stored and parsed, and it can be queried with Elasticsearch. And performance issues occurs in the process because the cluster is very large. So this is handled by another separate team. But I think this is out of the scope for today's topic. I think that a separate team will be monitoring that.
Thank you very much. It's not stratified structure, so I understand that. And cold data is objective storage, so it will be stored. And for that cluster, is there a possibility of further stratification? As for the cluster that we built, the storage capacity is meant to grow, and the data storage cost could become a problem. So the costly data will be stored in a separate coding so that we can save cost, and so that we can respond to the cost issue of the cold data. As for now, it's not. We are thinking of cold archiving the cold data.
Well, thank you very much. So depending on the object size, it is stored in HDD or SSD or replica. I think this enough. This is a good system on its own merit. I think this is a great system. I hope that we could collaborate further going forward. And this is about operation, version upgrade. Maybe about version upgrade. Do you have any ideas on version upgrade that does not cause clusters, that not affect clusters? Well, we can do it without affecting the clusters. We have done that as we operated our Cephs, and we do have a lot of experience on that. So we can build up on that. The object storage is working based on Ceph cluster, and the version up can be done seamlessly.
But I think there is some time issue. If you do the version upgrades, it will take a lot of time. Thank you very much. I guess that would be true because of the scale. I think it's difficult to operate such a large scale. I have a question about security. Object HTTX is how you access it. How do you do the data encryption? As for S3 spec, SSCE, so from the client side, they have the encryption key and they encrypt the data from their end. So we are using SSCC. So they just have the key and it is stored in an encrypted format.
Thank you very much. Encryption is a very important topic for Yahoo Japan.